Question 16 says a slit of width A is illuminated by a red light of wavelength lambda equal to 650 nanometer. Find the value of A if the first minimum appears at theta equal to 15 degree and the value of sine 15 degree is given as 0.259. Well, the question is based on the topic diffraction, and we know that for the first minimum the expression that we have is A sine theta equals lambda. In fact, for nth minimum we have equation A sine theta equals n lambda, and the value of n is 1 for the first minimum, right? So we have to find the value of A, which is the slit width. Lambda of course is the wavelength, and theta is the angular position where we are looking at the diffraction pattern. Okay, so the value of A is then lambda by sine theta. The value of lambda is given, this is 650 nanometer, and the value of sine theta is, so here we have 0.259. This means that the value of A is 650 into 10 to the power minus 9 meter by 259 into 10 to the power 3. So this in meter in fact is the value of A. Now what we see is that this is quite close to 2.5 micrometer, because we have 10 to the power minus 6 meter, so that in fact is micrometer. So the slit width is coming out to be 2.5 micrometer or 2.5 micron. That means option 4 is correct for question 16. Let's now go to the next question. Question 17 says light of wavelength 400 nanometer falls on a metal having work function 2.0 electron volt. The maximum magnitude of the linear momentum of photoelectron emitted is nearly, and the 4 options are given. Well, this is based on photoelectric effect. So let's start solving. First of all, we find the energy of the incident photon, and that energy E is given as hc by lambda. We can take the value of hc as 1240 electron volt nanometer. So this is 1240 divided by 400, and now we have it in electron volt. So this is further 3.1 electron volt. That is the energy of the photon, 3.1 electron volt. So that means the most energetic photoelectron has energy equal to 3.1 minus 2, that means 1.1 electron volt. So that means energy of the photoelectron, and let's call it EPE, and in fact the maximum value is 3.1 minus 2, or simply 1.1 electron volt. Now this is the kinetic energy, and we know that momentum and kinetic energy are related like this, that energy in fact is P square by 2m, where P of course is the momentum. So that means the momentum can be written as under root of 2 times mass into kinetic energy. So we have the values now. The value of m we can take as 9.1 into 10 to the power minus 31 kg, which is in fact the mass of electron, and the value of E we already have. We shall put everything in the SI unit. So the momentum of the photoelectron, in fact the maximum magnitude of momentum of the photoelectron would be 2 times 9.1 into 10 to the power minus 31 kg, and the value of E is 1.1 electron volt. So if we convert this into SI units, we need to multiply it by 1.6 into 10 to the power minus 19, and this of course will be in SI units, which is kg meter per second. So now it's a matter of simplifying this, and if we simplify this, well, we can see that this is about under root of 32 into 10 to the power, we can take the square root of 10 to the power minus 50 easily, which is what we shall get when we multiply 10 to the power minus 31 with 10 to the power minus 19. So this is then 10 to the power minus 25 outside the radical sign, outside the square root sign. And further simplification gives us the value of P as 5.7 into 10 to the power minus 25 kg meter per second. So we have done a little bit of approximation. Well, that is fine, and in fact no other option is close by to. That means option 3 in fact is correct. So when I said no option is close by, I mean other than option 3, no other option is close by. So option 3 is correct for question 17. Time now to go to the next question. So we are now at question 18, which says an electron projected perpendicular to a uniform magnetic field B goes in a circle. Assuming Bohr's quantization rule for angular momentum, the radius of the nth orbit will be. Symbols have their usual meaning. Well, we know that when a charged particle is projected perpendicular to a uniform magnetic field, the path of the particle is circular and the particle is in uniform circular motion. So this question in fact combines the concepts of magnetism, the concept of motion of a charged particle in a uniform magnetic field, as well as Bohr's atomic model. And from Bohr's atomic model we have to take the Bohr's quantization rule. So let's start with the solution now. And well, as far as motion of the charged particle is concerned in a magnetic field, we have the equation that radius in fact is given as mv divided by qb. So m of course is the mass, v the speed, q the charge, and b the magnetic field. Now in this particular case, the radius of the electron will be given as mass of electron into its speed v divided by small e, which is the magnitude of charge on the electron, and the magnetic field B. So this is the radius. Now if we look at the Bohr's quantization rule, we have angular momentum mvr as nh by 2 pi, and we are supposed to find the radius of the nth orbit. So between these two equations we can equate v, so v will get eliminated and we can have the required expression. So from the first one, the value of v is EBR divided by m, and from the second equation the value of v is in fact nh divided by 2 pi mr, and that means we have r square equal to, well, the m goes off, the value of r square is nh by 2 pi into e into b, and that means the expression for radius is then n under root of nh by 2 pi eb. Let's look at the options. We can see that it is matching with option 4. So option 4 is correct for question 18. Time now to go to the next question. Question 19 says a capacitor of capacitance 50 microfarad is charged to some potential and then the plates are connected through a resistor R. A radioactive sample decays with an average life of 40 milliseconds. Find the value of R if the ratio of the charge on the capacitor to the activity of the radioactive sample remains constant in time. We can see that the question combines the concepts of radioactivity with decay of charge in a RC circuit. So let's start with the expression for charge on the capacitor when the charge is decaying, and that expression in fact is Q is equal to initial charge Q naught into e to the power minus t by time constant, which is in fact RC. So this is the charge on the capacitor, and let's now look at the activity of the radioactive sample is given by A is in fact equal to lambda n, and the value of n can be given as n naught e to the power minus lambda t, where n naught is the number of radioactive nuclei at time t equal to 0. So now if you look at the ratio of the charge on the capacitor to the activity of the sample, well, that ratio is then Q naught e to the power minus t divided by RC divided by lambda n naught e to the power minus lambda t, and this ratio has to be independent of time. That means Q naught by lambda n naught, and well, this particular ratio of course is independent of time, but the other term would be t into lambda minus 1 by RC. Now for this value to remain constant, the coefficient of time t must be 0, which gives us that lambda is equal to 1 by RC, and we are supposed to find the value of R. So the value of R can be given as 1 by lambda c. Lambda of course is the decay constant. What we have been given is average life. In fact, average life is 1 by lambda, so that means the value of resistance will be 40 into 10 to the power minus 3, and the value of C is given as 50 microfarad, so this is 50 into 10 to the power minus 6. Now we see that this will in fact come out to be 800 ohm. So this in fact is in ohm, and the value of resistance is 800 ohm. That means option 1 is correct for question 19. Let's go to the next question now. Question 20 says the logic operation performed by the circuit shown is, and this is the circuit given to us. Options are not, and, or. Well, we can see that the first one in fact is a NOR circuit, and the output of this NOR circuit is going into the other circuit, which effectively is a NOT circuit, because if we have 1 coming here, we shall get 0, and if it is 0 coming here, we shall get here as 1. So a NOR followed by a NOT circuit will effectively be an OR circuit only. So the answer is straightforward. Option 4 is the correct one. That means question 20 is done. Time now to look at the next question.